the variables. Now the temperature coefficient of ISC, we will call that as R. Let us try to understand the temperature coefficients better by doing some examples. But before that, let us name the variables. Now the temperature coefficient of ISC, we will call that as alpha I. The temperature coefficient of VOC, we will call that one as alpha V. And the temperature coefficient of peak power as alpha P. For this particular example, you see that the temperature coefficient of current is 0.045% per degree Kelvin, and temperature coefficient of VOC is minus 0.34% per degree Kelvin, and that of the power alpha P is minus 0.47% per degree Kelvin. So what do these numbers mean, and how do they affect the overall voltages, currents, and the power? And that's what we would like to see now. Consider the IV characteristics as shown here. Let the IV characteristic, which is in red, represent the characteristic at temperature 25 degree centigrade or 298 degree Kelvin. So this is the standard temperature, and the one in green, let us say it is at 40 degrees centigrade. Now we know from the data sheet the open circuit voltages and the short circuit currents at standard temperature and insolation, and this value from the data sheet is given as 36.72 volts, and ISC is given as 8.99 amps, all this from the data sheet. Now we need to find what is VOC at the 40 degree curve and also ISC for the 40 degree curve. The peak power for the curve at standard temperature and insolation is given as 240 watts peak for this particular cell in the data sheet. We need to estimate what is the peak power value for the curve which represents the 40 degree centigrade temperature. Let me replace the question marks by meaningful variables. So what we need to estimate is here the short circuit current at 40 degree C, the peak power at 40 degree C, and VOC at 40 degree C. ISC short circuit current at 40 degree centigrade is equal to the short circuit current at the standard temperature 25 degree centigrade plus delta I. Likewise, VOC at 40 degree centigrade is VOC at 25 degree centigrade standard temperature plus a delta V. And the power, max power or the peak power at 40 degree centigrade is given by the peak power at the standard temperature of 25 degree centigrade plus a delta P. We need to find what the delta I, delta V, delta P values are using the data sheet temperature coefficient parameters. The temperature coefficient of ISC, alpha I, is given as change in ISC divided by ISC at standard temperature into 100. So which means that this whole thing is converted to a percent form per degree change in temperature. So this is how it is defined as per the data sheet, and this value for the short circuit current we saw is given as plus 0.045% per degree Kelvin. Rearranging change in ISC, which we shall denote as delta I, is given as alpha I, the temperature coefficient of ISC, into the ISC at standard temperature of 25 degrees centigrade into delta T, the change in temperature, divided by 100. Amps. So this would be the change in ISC. Now substituting it in the ISC equation, we find ISC at 40 degrees centigrade is equal to ISC at 25 degrees centigrade plus a delta I. The delta I can be replaced like this. Alpha I is the temperature coefficient of ISC as given in the data sheet into ISC at 25 degrees centigrade, reference temperature, into delta T, difference in temperature, by 100. If you take out ISC at 25 degrees centigrade out as a common factor, you will get this particular term, 1 plus alpha I to delta T by 100. For the values given in the data sheet, substituting for all these parameters here, we can get the short circuit current ISC value at 40 degrees centigrade. ISC at 25 degrees centigrade, 8.99 amps as given in the data sheet. Alpha is 0.045% per degree Kelvin. Temperature, the standard temperature is 25 degrees centigrade and the raised temperature is 40 degrees centigrade divided by 100, and that would give you a value of 8.9968, 0.0068 amps higher than the corresponding current value at 25 degrees centigrade. Along similar lines, the open circuit voltage at 40 degrees centigrade is given by the open circuit voltage at the standard temperature of 25 degrees centigrade plus a change in voltage delta V. Now this change in voltage delta V can be obtained using the datasheet value of temperature coefficient of VOC into the VOC at 25 degrees centigrade into the change in temperature by 100. Removing out the common factor, the VOC at standard temperature into 1 plus alpha V to delta T by 100. So if we substitute the values from the datasheet values, 36.72 volts for the VOC at standard temperature, alpha V for the VOC is given as minus 0.34, note the minus because the VOC decreases with increase in temperature. A temperature rise of 40 minus 25 degree, which is 15 degrees centigrade, divided by 100. So this amount here amounts to minus 0.051, which pulls down the open circuit voltage to 34.847 volts. So as temperature increases, the open circuit voltage will drop. Similarly, for the peak power value also, Pm at 40 degrees centigrade is given by Pm at 25 degrees centigrade plus a delta P value. The delta P value can be expressed as alpha P, the temperature coefficient of peak power, into Pm at 25 degrees centigrade into delta T by 100. Simplifying, we have Pm at 25 degrees centigrade to 1 plus alpha P delta T by 100. Now, if you substitute the datasheet values, Pm at 25 degrees centigrade is 240 watt peak. 1 plus alpha P from the datasheet is given as minus 0.47 into 40 minus 25 degrees centigrade rise in temperature by 100. This portion will become negative. It is minus 0.0705, which will pull down the value of the peak power to 223 watt peak. Therefore, here again you observe that with rise in temperature, the value of the peak power will come down.